I'm going to talk to you about nanoparticles and some toxicological effects caused by nanoparticles. To start, I would like to introduce nanotechnology and how this field has influenced all of us. I'll explain what nanoparticles are and how their properties can lead to toxicity by distribution throughout the body. We will see some examples of how certain nanoparticles can cause pulmonary and cardiovascular toxicity, genotoxicity, neurotoxicity, dermatotoxicity, cytotoxicity, and ocular toxicity. Very briefly, we will look at a few environmental impacts from nanoparticles, and I will conclude with some general thoughts. Nanotechnology is a relatively new science. In 1959, Richard Feynman, a US physicist and Nobel Prize winner, presented the concept of creating nanoscale machines to manipulate, control, and image matter at atomic scale. Nanotechnology has caused a scientific revolution. So what exactly is nanotechnology? Nanotechnology is often referred to as molecular manufacturing, which involves the manipulation of matter at atomic, molecular, and macromolecular scale to create new structures, materials, and devices. This is done at a scale of 1 to 100 nanometers. A nanometer is 1/1000th of a meter. The average human hair is approximately 25,000 nanometers wide. Let's think about this in terms of entry into the body. Nanoparticles are approximately the same size as viruses and tobacco smoke, which can enter the body through the lungs relatively unimpeded. The new discovery of how elements and chemicals behave on the nanoscale has opened a scientific gateway with a projected growth into a $1 trillion industry, transforming the development of a myriad of consumer products, medicine, as well as thousands of other industrial processes. The fundamental basis of nanotechnology starts with the synthesis of engineered nanoparticles, particles measuring less than 100 nanometers. From there, nanoparticles are used to manufacture nanomaterials, which takes on large variations in shapes and sizes. For an example, nanofibers can be engineered to form long, hollow nanotubes or long, solid nanorods. Nanomaterials are arranged into functional units that construct the desired end product. The lowest level are nanoparticles, which are grouped to form nanomaterials and further manufactured to consumer products like sunscreens and electronic displays. Nanomaterials are also found all throughout nature, like the arrangement of nanofur on the gecko footpad, providing highly adhesive properties, enabling geckos to climb vertical surfaces like walls and windows. Mimicking properties found in nature has allowed nanotechnologists to engineer functional systems into products with unique and revolutionary properties. The application of nanotechnology in our everyday lives is enormous. Nanotechnology is used in thousands of consumer products like cosmetics, electronics, sensors, paints, sporting goods, and the list continues. Nanotechnology has influenced many applications in very beneficial ways. For instance, in medicine, new drug delivery devices allow for efficient delivery of drugs with fewer adverse side effects. In the future, and still very much theoretical, nanomedicine proposes the potential of diagnosis and treatment at a molecular level, detecting and treating pre-symptomatic diseases, rebuilding neurons in neurodegenerative diseases like Alzheimer's, and bone regeneration in individuals who do not receive rehabilitation. Nanomembrane filtration systems are offering new ways to clean water at affordable prices, and nanotechnology also promises cleaner and more efficient ways to capture and generate electricity. Nanoparticles have enormous implications in our lives, but do we really understand enough about nanoparticles to warrant their use in such an expansive array of applications? Nanoparticles occur naturally as well as made by man. A little later in my presentation, I will mention some studies which found toxicological findings based on these specific man-made nanoparticles. Materials at the nanoscale begin to exhibit unique physical and chemical properties that are clearly different from the same molecules at a larger scale. This phenomenon is known as the quantum size effect. Nanoparticles have a much higher ratio of surface area to volume that results in changes in mechanical, thermal, and catalytic properties. For an example, gold and silver are inert. However, at the nanoscale, gold becomes combustible while silver takes on antimicrobial properties. Copper, an opaque substance, becomes transparent. Platinum, an inert material, becomes a catalyst. Aluminum, a stable material, turns combustible, and silicon, an insulator, becomes a conductor. Nanoparticles are engineered and created with specific sizes, shapes, surface features, and chemistry. Their unique physical-chemical properties are also likely to produce unique bioactivity. From a toxicological standpoint, understanding the relationship between nanoparticles' properties and bioactivity serves as an essential tool in the prediction of relative pathogenicity of any given nanoparticle. The following physical-chemical properties are believed to be important determinants of biological responses. Particle size appears to be a major factor in biological responses to nanoparticles. Certain shapes have shown to result in more toxic significance. For an example, long, thin nanotubes are significantly more toxic and induce a greater inflammatory response. Both particle size and shape affect the ability of a particle to penetrate membranes and enter tissues. Some nanoparticles have a greater ability to generate reactive oxygen species and cause oxidative stress on biological systems. Surface functionalization refers to how the nanoparticle will interact with the surfaces of biological systems. The rate of dissociation of a nanoparticle will influence how much is transported to systemic organs and cleared from the body. Exposure to nanoparticles can be simplistically expressed as occupational exposures during the manufacturing of products, public exposure to those products, and environmental exposures, which sadly is most often neglected. Not every nanomaterial is dangerous to human health and safety. Three of the most influential aspects on nanoparticle toxicity include shape, reactivity, and size. These aspects influence the potential toxicity of nanoparticles because they largely dictate how readily they gain access into the human body, the ease of transportation throughout the body, and how they behave once inside. Smaller size, given a specific shape and reactivity, generally means they will gain entry into the human body more readily, causing a greater potential to be toxic. This may be the case because as particle size decreases, given the same mass per volume, the dose in terms of particles increases. The respiratory system, skin, and intestinal tract are always in direct contact with the environment. These organs are the first entry points for nanoparticles. The smaller the nanoparticle, the specific shape and reactivity also determines its mobility within the body. Highly mobile particles are very dangerous as it can be distributed throughout the body and enter cells, tissues, organs, and in some cases even cross the blood-brain barrier. The behavior of nanoparticles, and thus the effects they cause on one's health, is a function of size, shape, and surface reactivity with surrounding tissues. Each nanoparticle acts differently due to its unique characteristics, but also the same nanoparticle can behave differently between species and individuals. The solid boxes represent biodistribution of nanoparticles in rats compared to mice. A wide range of health effects have been associated to nanoparticles. Some nanoparticles can enter cells causing cytotoxicity, while others accumulate and impede biological systems. I want to touch upon some general examples to demonstrate some possible types of toxicity from nanoparticles. In one study, inhalation of primary combustible derived nanoparticles, predominantly from automobiles, generated more free radical molecules, activating pro-inflammatory mediators leading to lung cell inflammation and damage. This led to decreased lung function. Asthma and chronic obstructive pulmonary disorders were intensified, and there was an increased incidence of lung cancer. Ultimately, combustible-derived nanoparticles was associated with an increased mortality due to respiratory and cardiovascular causes. They postulated that combustible-derived nanoparticles created oxidative stress. The oxidative stress caused a series of reactions leading to pulmonary inflammation and cardiovascular effects. In another study on diesel exhaust, there is an association with inflammatory responses in the pulmonary system and airway hyperactivity. They observed that the cardiovascular system's ability to vasodilate is significantly impaired following the exposure of diesel exhaust. Each graph shows a common vasodilator. On the y-axis, we have forearm blood flow. The closed circles shows the change in forearm blood flow following exposure to diesel exhaust. short-term inhalation of ultrafine carbon black particles leads to inflammation, oxidative stress, and changes to a coagulation system. Long-term exposures causes chronic pulmonary inflammation, pulmonary fibrosis, and increased risk of lung tumor. Titanium dioxide, often used in paints, sunscreens, and even food coloring, were found to overload lung cells in studies performed on rats. Carbon nanotubes are used in electronic displays, casts, superconductors, purifying water and oil, and for structural support in sporting equipment, body armor, vehicles, and buildings. Exposure to carbon nanotubes may lead to similar effects as asbestos, namely mesothelioma, a cancer in the lining of the lungs. Fullerenes caused oxidative stress, and silver nanofibers are suspected precursor for lung cancer. Genotoxicity of nanoparticles is somewhat inconclusive. There are studies that show genetic alterations and other studies which seem to disprove these findings. One study on nanotitanium dioxide, primarily used in sunscreens, showed an association with DNA mutation and chromosomal damage in mice. They postulated that nanoparticles led to oxidative stress, causing a series of reactions which influence DNA. Similar to genotoxicity, neurotoxicity is difficult to study and needs to be further investigated. Acute toxicity may be unlikely except in extreme circumstances, but chronic toxicity might occur, and indeed, the etiology of many neurodegenerative diseases is considered to involve interactions between genetic factors, aging, and some environmental factors like nanoparticles. Many dermotoxicological studies indicate that nanoparticles can interact with biological systems. The composition, size, and surface properties are important attributes that are needed to predict biological effects. In one study, they applied quantum dots topically to the skin. Quantum dots are used in sunscreens and other cosmetic products. They found penetration of intact stratum corneum to the viable layers of the epidermis, and in some cases the dermis, within 8 to 24 hours, shown by the white arrows. Nanoparticles can be internalized in cells and act on the mitochondria, nucleus, cytoplasm, membrane, and even lipid vesicles. Magnetic nanoparticles have been used as contrast agents for MRIs and are FDA approved for such use systematically. Iron nanoparticles were administered to the eye, and there is little to no signs of inflammation, retinal degeneration, and minor changes to the retinal pigment epithelium, with no detectable increases in oxidative stress with any treatment group. In another study, cerium oxide nanoparticles protected cultures of rat retinal neuronal cells from hydrogen peroxide-induced cell death. Furthermore, cerium oxide particles also protected against photoreceptor damage. Nanoparticles are being released into the water and air during production, waste byproduct of production, disposal of products containing nanoparticles, and they accumulate in soil, plants, animals, and water. So what happens once these nanoparticles accumulate in the environment? Fullerenes cause damage to fish and water fleas. Japanese rice fish accumulated high concentrations of nanoparticles throughout their body. This could quite possibly lead to biological accumulation. The nanoparticles were found in the eggs of their offspring. Silver nanoparticles that were used in socks to reduce foot odor were released into wastewater after washing them. The nanoparticles prevented the multiplying of bacteria found in natural ecosystems and waste treatment processes. The nature of working at a nanoscale, 1/1000th of a meter, brings forth immediate challenges. Observing and understanding at such a small scale is difficult. Biological systems are still not completely known at this scale, making it even more difficult to understand how nanoparticles interact with these biological systems. Materials at this scale also behave differently than expected. The majority of research in nanotechnology is for developing or improving applications. These advances will revolutionize aspects of certain fields and can be used to make substantial profit. Organizations are more concerned with being the first to set stakes with such emergent sciences for profitability, but a much smaller concern is placed on environmental, health, and safety concerns. Nanotoxicological research is being shortchanged. These studies require precise characterization and properties of any given nanoparticle, as any variation can lead to differential toxicological properties. New nanoparticles and nanomaterials are being created at such a rate that nanotoxicological research cannot keep up. This emerging field of nanotoxicology must continue to grow as new products are continuously produced. In summary, manufactured nanoparticles present unique and amazing possibilities. But adjacent to the benefits come the downfalls. There are no set exposure limits, no material safety data sheets that we can reference. In fact, there is a serious lack of information about human health and environmental impacts from manufactured nanoparticles. The uses for nanotechnology in so many fields also brings additional risks and new classes of problems. So we won't know the best way to assess, recognize, control, or prevent human exposure to nanoparticles, nor will we be able to protect against the risk that may or may not be associated with them.